Work and energy starts to get kind of gnarly because there's lots of things going on, as we'll see in this problem. From 3.4, number 18, a 5 kilogram box slides down a 5 meter high frictionless hill starting from rest across a 2 meter long horizontal surface, then hits a horizontal spring with a spring constant 500 newtons per meter. The other end of the spring is anchored against a wall. The ground under the spring is frictionless, but the 2 meter long horizontal surface is rough. The coefficient of kinetic friction of the box on the surface is 0.25. So many things going on, and there is no single equation which is going to solve all this because there's lots of different segments. So, as is often the case, a diagram will help us figure out what on earth is going on here. So let's start with the hill. We've got a hill, 5 meters high, then it goes across a horizontal surface, which we have been informed is rough. So I'm going to draw a little rough surface, and then it hits a spring, which is attached to a wall, and the surface underneath the spring is smooth. So I'll indicate that with a nice smooth line. And this is our box. Our box will be orange. Our box is going to slide down from here down this ramp with a height of 5 meters. It is then going to completely not to scale, then is going to slide a distance along here of 2 meters plus whatever it compresses this spring by. We're going to call that X. And so let's break this down one thing at a time. What is the speed of the box just before reaching the rough surface? All right, so that is the box just descending the hill. Let's see if we can make this a little smaller and kind of tuck it out of the way. There we go. All right, that part is relatively straightforward. We've just got a box on a frictionless slope. We've got gravitational energy here, and we're going to have kinetic energy here. So that's just a conversion of gravitational to kinetic energy. And so we've got mgh turning into 1/2 mv squared. Get rid of the masses, so gh will be 10 times the height of 5 equals 1/2 v squared. V is going to be the square root of 100. Wasn't that nice? So the velocity is going to be 10 meters per second. All right, part A, piece of cake. What is the speed of the box just before hitting the spring? All right, well, throughout this section of the movement, it's going over this rough surface. And so while there is a displacement in the positive direction, just displacement to the right, there's going to be a force of friction acting on it to the left. And I regret making the choice to draw displacement as an arrow, made it look like a force. I'll draw it down here. So there's a displacement to the right and there's a force to the left that is going to be doing negative work. It's going to be withdrawing. It's going to be taking out some energy from the motion of the box. And it's only going to be for that distance. We know exactly how long that is because as soon as it hits the spring, it's on a frictionless surface. So it doesn't continue to lose energy once it gets there. It's only along that rough surface, which is 2 meters long. So the work done is going to be that friction force times that distance, and the work done across that segment will be, well, the friction force is going to be mu times the normal force times distance. And because this is a horizontal surface, mg down and normal force up, normal force will equal mg. So we can say that the work done is going to be u mgd, mu mgd. So we got a grand total. I mean, we know all these values. So mu is 0.25, mass is 5, gravity is 10, distance is 2. So we got 5 times 2 is 10, times 10 is 100, a quarter of 100 is 25 joules. So as it passes that rough section, 25 joules of energy are going to be lost because it's friction, so it's going to be, and it's acting in the opposite direction of the thing's motion, so that's energy that it's losing. So we've got kinetic energy here. Let's apply some numbers. Let's call this location 1, location 2, location 3, and location 4. That's where the spring will be fully compressed. So so we've got kinetic energy at location 2 plus any work that's going to be done will tell us how much kinetic energy there will be at location 3. And what I'm realizing is I've failed to acknowledge numerically the negativity of the work. So if we were being explicit, we'd say it's FD cos theta, where theta is 180 degrees. So that would be times cos of 180. So that would be cos 180. So that'd be all that times -1. So the work done is in fact negative 25 joules. So we've got some kinetic energy at the bottom of the slope, which we didn't actually calculate explicitly, but that was the same as the potential energy at the beginning. So we could say that the potential energy at the beginning becomes that kinetic energy at the end. So what is that? That's mgh. So that's going to be 5 times 10 times the height of 5. So that's 5 times 5, 25 times 10 is 250. All right, so kinetic energy is 250 joules plus the work being done, which itself is negative 25 joules. And that is going to give us the resulting kinetic energy at the moment that it hits the spring. So 250 minus 25, well, that's 225 joules of kinetic energy is equal to 1/2 mv squared at location 3. So just got to crunch a number there. 225, this calculator doesn't work. 225 equals 1/2 times the mass, which is 5b squared. 2 divided by 5, square root of, is 9.48, 9.5 meters per second. About 9.5, not negative, 9.5 meters per second. All right, so I gotta shrink some things up because we're filling up all of our available space. We still have to figure out how far the spring is compressed. All right, so let's shrink you all up. So this all pertains to part B. So between points 3 and 4, well, at point 3, we've now just figured out how much energy there is after the rough slide. So the kinetic energy at point 3 is 225 joules, and that entirely is going to turn into spring energy at point 4. So this becomes one of our easier calculations. We've got kinetic energy 225 equals to 1/2 kx squared, and conveniently we are told what the spring constant is. So it's 225 equals half of 500 times x squared So we've got 225 over 250 equals x squared, square root all that. The compression is going to be 25 divided by 50. 0.95 meters. All right, so it compresses by 0.95 meters. And that is part C. And lastly, the question asks, including the first crossing, how many complete round trips will the box make before coming to rest? All right, well, I like this idea of crossing. Imagine yourself as a swimmer, and you've got to go from here to there, and to get from here to there, you have to use up a certain amount of your energy. When you've used up all your energy, you're just too tired to continue. And so we've already found that one crossing is going to absorb or withdraw 25 joules of energy. So every time you do a crossing, you're going to lose 25 joules of energy. Well, we started with 250 joules, so we're going to be able to do 10 crossings. That's 10 crossings, but then the question asks, how many complete round trips? Well, that's 10 crossings, and a round trip is 2 crossings, so that would be 5 round trips. And by the end of the 5th round trip, you will have completely used up all of the energy. The end.